Hello, in the previous video we showed how the coefficients of a Cartesian form of a Cartesian equation of a plane are the normal vectors of the plane, but now we're going to derive how that actually works out. So assume we have, let's say we have a plane pi, and this is the normal vector that's perpendicular to the plane, right? And then we'll let the normal vector right here have the components a, b, and c, and then we'll have some vector in the plane that's in the plane AB, right? And then if we let A be the position vector with coordinates x1, y1, z1, and B could be any other point in the plane, x, y, z, right? So that means we can go ahead and write, yeah, let's do this. AB can be represented as the vector x minus x1, y minus y1, and then z minus z1, right? Good. And since the vector, this represents every possible vector basically in the plane, right, depending on what point B you pick, and since they are perpendicular, then we know we know that the normal vector is going to be perpendicular to every vector in the plane, so I know that vector AB dot product the normal vector, that's going to be equal to 0. And then since AB is x minus x1, y minus y1, and then z minus z1, the normal vector has components a, b, c, that's going to be equal to the 0 vector, right? And then I can apply the dot product to this, right? And let's do it this. I can say a times this, so it'd be a times x minus x1 plus b times y minus y1, and then c times z minus z1. That's all going to be equal to 0, right? And then I distribute this out, and I'll have a times x minus a times x1 plus b times y, b times y minus b times y1 plus c times z minus c times z1, and that's all equal to 0. And then I can solve for, get all the x1, y1s, and z1s to the right-hand side, and I'll end up with the equation ax plus by plus cz. Good. And then I'll have ax1 plus by1 plus cz1, right? And I can go ahead and see a few things that happen out of this. Well, we usually these are just some constant numbers, so we just let that equal some constant d, and then ax plus by plus cz, and we can see that these numbers a, b, and c, they are the coefficients of the equation of a plane, and those a, b, c correspond to the normal vector in a plane. Another thing that we notice that we can get out of this, if we look at this one, if we take x, y, z and dot product with a, b, c, which is our normal vector, right, we get this side of the equation. And on this side of the equation, if I do the same thing, but with the position vector x, y, x1, y1, z1, and also multiply it by a, b, c, right, we can get the vector equation of a plane this way. And the way that we write this out, this here is r, that's our vector r. ABC times our normal vector is going to be equal to a, this is our position vector x1, y1, z1 times this. So basically, if we know we know the normal vector and we have a point in the plane, we can write an equation of a plane that way, given this formula right here. Sound good? And that's what we're going to do in our next problem. So if we go ahead and look at this problem here, it says find the equation of a plane pi which contains the point. We got a point and is normal to the vector, this guy, right? So I can use that equation that I just derived, where vector r times the normal vector is equal to our position vector times our normal vector, right? So r is equal to x, y, z, right? Those are going to be every point in the plane, the normal vector. If it's normal to this, right, then it's going to be 2, negative 1, 1, 2, negative 1, negative 1 is going to be equal to our position vector, which would be negative 1, 1, 2. And then our normal vector, it should be 2, negative 1, negative 1, right? And then here I can do the dot product, so it'd be 2x minus y minus z is equal to negative 2 minus 1 minus 2, which is going to be negative 5, and then 2x minus y minus z. So there you go. Here is our equational plane that has this normal vector, right, and has that point. So that's it. And then it says, hence show that this point right here, 0, 4, 1, is on the plane. So our x-coordinate, so that would be 2 times 0 minus 4 minus z, which is 1, and that has to come out to be negative 5, and then this is 0, so that's gone. Negative 4 minus 1 equals negative 5, and negative 5 equals negative 5. So yes, this point right here is on the plane that we have there. Sound good, guys? Thanks.